All right, welcome back, everyone. Today, we're diving straight into the engine room of modern software engineering. We've got a brand new explainer covering how to build a lightning-fast, highly reliable CI/CD pipeline specifically tailored for robotics projects. If you've ever found yourself sitting around waiting 20 or 30 minutes for a pull request just to tell you that a simple test failed, you absolutely know the pain we're trying to solve today. We're going to map out an entire automated DevOps stack, from GitHub Actions workflows and caching strategies to a multi-stage Docker setup in GHCR releases. Here's our roadmap for today. We'll kick off with the pipeline philosophy, break down the anatomy of CI workflows, and explore caching for fast builds. Then, we'll walk through a pretty wild merge queue war story, unpack multi-stage Docker releases, and finally, look at some lessons from the gate. Let's get right into it.
Section 1. The pipeline philosophy. Speed and reliability as features.
So the core mindset driving this whole architecture is actually pretty fascinating. The pipeline is the product. It perfectly sets the stakes, right? I mean, a robot you can't reliably ship is, at the end of the day, just a liability. Think about it. A slow 25-minute continuous integration process absolutely kills developer momentum. If your team has to wait that long, it essentially becomes a pipeline nobody even wants to run. Speed and reliability aren't just optional nice-to-haves. They are foundational features.
And that brings us to this crucial point, a hard rule, literally hard-coded right into the YAML file, 10 minutes. If a build ever creeps past that 10-minute ceiling, GitHub is instructed to just kill it. The PR goes red, no soft warnings, no maybe next time. It's a strict budget. We aren't budgeting for infinite hangs, we are budgeting for rapid, actionable feedback.
Moving on to Section 2, Anatomy of CI workflows, one workflow, two jobs. Looking at the mechanics here, we've got a single workflow with a required lint build test job. And it's laid out in exactly 9 steps to build a rock-solid gate. It sequences everything perfectly. It starts with installing build tooling and checking out the PR. Then, it moves into caching the Mujako SDK, fetching it on a miss, and registering it with the linker. After that, it caches Ccache, runs rowstep install to catch missing dependencies, builds everything with CallCon, and finally hits step 9, CallCon test. That final step is the actual gatekeeper that matters, catching those sneaky syntax and semantic errors.
Now, here is a major architectural decision, and honestly a massive pro tip. You might be tempted to use a naive Docker build approach for your CI, but using the containers job strategy is just functionally superior. Why? Well, first, you get direct access to your artifacts, no doing weird volume gymnastics or running Docker CP commands to grab your logs and recordings. Plus, the iteration is way faster, since the base image is pulled once and the build happens directly in it, rather than rebuilding a bunch of Docker layers. And third, you are testing exactly what you ship, using the exact same base image your release is going to use. It's a total game changer.
All right, Section 3, Caching for fast builds, surviving the 10-minute ceiling. To actually stay under that strict 10-minute budget across dozens of runs, you need a strategic caching plan. Get this, a cold build after a cache eviction takes about 6 minutes, but a warm build? Just 80 seconds. 80 seconds. With a feedback loop that tight, developers can check their CI status as casually and quickly as checking a Slack message. How do they pull that off? By leveraging 2 very distinct caches. First up, the Mujako SDK cache. This one uses a fixed key because the SDK version is pinned, so a hit is basically free and shaves off about 30 seconds of downloading and extracting. Second, and most importantly, the CK cache. This one is keyed by the commit SHA. It provides a precise cache slot for every single run, turning what would normally be a grueling 4-minute C++ compile into a lightning-fast 20-second link. This dual caching strategy is the magic bullet for surviving that 10-minute ceiling. Next up, Section 4, Merge Queue War Story, debugging the undocumented. So setting up a native merge queue was a huge win for reliability. But man, it triggered a wild 3-act troubleshooting saga. Act 1. The maintainer tried to enable it on a personal private repo. The result? The API throws a 422 unprocessable entity error with a completely empty body. Just no hints at all. Act 2. Thinking it was a visibility thing, they make the repo public. Still an empty 422 error. Act 3. Finally, they transfer the repository under a GitHub organization account. Boom. Suddenly, the exact same API call returns at 200 OK, and the queue functions perfectly. The culprit? A completely undocumented constraint. It turns out the native GitHub merge queue strictly requires the repository to be owned by an organization account. It had absolutely nothing to do with public versus private code. It was strictly the account type. Discovering that little quirk, which wasn't documented in the error path anywhere, was the key to finally getting those merges serializing safely.
All right, Section 5, Multi-Stage Docker Release, Packaging the Robot.
With the code tested and merged, it's time to safely package the final release. We're looking at a highly optimized Fat Builder versus Slim Runner setup here. The Fat Builder uses a ROS base image with the full toolchain and SDK to do all the heavy lifting and run unit tests. But, and this is key, you don't ship that. You ship the Slim Runner. This stage uses a much smaller ROS core base, which effortlessly strips out about 200 megabytes of bloat. It only brings along the essential runtime libraries and the final install tree copied from the builder.
There's a brilliant trap to watch out for here, dubbed Bug 5 by the author. In an earlier version, a required ROS package was accidentally left out of the Docker file's copy list. Here's the catch. ColtCon build inside Docker will completely ignore missing source packages. It just silently builds whatever is there. So they got a perfectly green build that crashed at runtime because it was missing a crucial navigation package. This is exactly why you absolutely must run your unit tests inside the Fat Builder stage before extracting your artifacts to the runner. Catch the missing package as a failed test, not a runtime crash on the actual robot. Once that final image is built, how is it tagged in the GitHub container registry? This setup triggers a slick 4-tag strategy off a single GitHub tag. You get your full semantic version for strict pinning, a minor track tag, a convenience latest tag, and most crucially, a short SHA tag. When things go sideways on the actual robot, that SHA tag ensures the operator knows the exact commit that's running. The tag literally is the commit, removing all ambiguity during incident response.
And finally, Section 6, Lessons from the Gate, Proving the Pipeline Holds. To prove this all works, the source material reviewed a 12 pull request history going through this exact pipeline. Take a look at PR6 and PR8. Both were intentionally broken to test the system. PR6 had a failing unit test. The pipeline immediately blocked the merge. PR8 passed unit tests but had a broken control gain, which ended up failing the headless software-in-the-loop simulation. The gate blocked the merge, and beautifully, it uploaded a ROS bag, a recording of the robot's data, as an artifact so the developer could debug it offline. We clearly see the pipeline successfully catching both simple syntax errors and deep semantic failures before they ever reach the main branch. Zooming out, one of the most powerful takeaways from building this pipeline is this 5-step fallback methodology for when you hit roadblocks, like that nightmare 422 error we talked about earlier. First, hit the constraint and read the error. Second, document it using an architecture decision record. Third, define a fallback to unblock the team right now, even if it's not perfect. Fourth, keep shipping on that fallback. And fifth, plan the actual permanent fix independently later. Basically, never let tool constraints stall your project's momentum. And that wraps up our explainer on building a bulletproof CI/CD architecture for robotics. From 80-second cached builds to multi-stage Docker releases, the tools are right there to supercharge your workflow. So I'll leave you with this to think about today. Is your CI/CD pipeline a fast, active gatekeeper? Or is it a slow, 25-minute bottleneck that your team actively tries to avoid? Think about that next time you push code. Thanks for tuning in, keep learning, keep optimizing, and we will see you in the next explainer.